this line, that line, that line. And that's how you're going to be able to calculate the normal stress and the shear stress at an arbitrary plane. This is going to be sigma n, and let's say that's going to be tau. But in order to understand what each of those circles are, it's not too difficult. This, for example, the circle between sigma 1 and sigma 3, it's all the possible state of stresses between the plane sigma 1 and the plane sigma 3 with planes that cut that cube and contain the direction of sigma 2. Can you see that? So all of those planes, they have the direction of sigma 2. The projection of the direction of sigma 2 in those planes is 0. If that's the case, then you can get what is all those state of stresses. And if you want to know what is this circle between sigma 1 and sigma 2, is going to be the opposite. Now you have planes which contain sigma 3, and for example, this is sigma 1, this is sigma 2, and all of the other planes that vary between sigma 1 and sigma 2 are going to be that circle, and for sigma 2 and sigma 3 are going to be the planes that vary from this location or this orientation to that orientation containing that direction of sigma 1. And that's going to be that circle over there. So we know what each of the circles are. So these lines I drew are possible state of stresses of a given normal stress and shear stress at that location. What about if there is a plane which does not coincide with any of the principal stresses? Where that state of stress is going to be? What do you think? It's going to be here, there, outside. So where is it going to be? On the lines? What do you think, Preston? You look like you have an answer.
So in between sigma 1 and sigma 3, you shade that region and lines.
Between sigma 1 and sigma 3?
Yeah, like the, I don't know what you call it, above the two arches.
Okay, above those two.
Yeah, do you shade that area and does it line up?
And all of these?
No, like still inside the circle.
Okay, inside, right? So inside or bound by those three circles, you have all the possible state of stresses for an arbitrary orientation. So here you can get what is sigma n and what is tau for an arbitrary orientation. How to compute that? Back in the days, people will figure out the angle between this and that, and then you trace like another circle, and I can tell you that one is complicated. I don't know how to do that. I know how to do it without an arbitrary plane, just going from a plane from here to there, or from here to there, from here to here, but I cannot do the oblique one. And you don't have to know that, how to do it graphically, but you need to know how to do it with multiplication of a tensor times a vector normal to a surface. And that's what actually you're going to do. We're going to do next week, and you're going to do on a homework that tries to calculate stresses for a given state of stress for arbitrary oriented fractures in order to see if those fractures are close to shear failure or not. but that's it. That's everything you have to know about the 3D Mohr circle. It's basically a graphical representation of all the possible state of stresses for a given tensor. Yes?
So are all those circles always perfect half circles with the diameter just coinciding with the distance between the principal stresses in terms of magnitude?
Okay, these are meant to be perfect half circles. And I'm just drawing the top because the other half is going to be exactly the same.
Oh yeah, no, I'm just making sure that it is actually that simple.
Yeah, those are just circles. And if you wanted to do it in 3D, you know, some people make like an ellipsoid instead of a circle, but that's a little bit more complex. Okay. Any question so far? No? Okay, this is one way of plotting a tensor. But still it's quite complicated, right? You wouldn't be able to plot like all these circles inside that. We need to simplify this a little bit more. And in order to do that, we're going to simplify the stress tensor just in two numbers, sometimes three, but our objective is going to simplify into two numbers. Okay. So in order to do that, we're going to decompose the Mohr circle, or to decompose the stress tensor. And before we do a decomposition mathematically, let's do a decomposition graphically. Let's say that I have a Mohr circle for a state of stress, and just to make it simple and to illustrate the concept, is just one Mohr circle in two dimensions, sigma 1 and sigma 2. This Mohr circle is telling us two things. One is telling us how far the Mohr circle is from the origin. And that tells you the magnitude of compression. And second is the diameter of the Mohr circle. The diameter of the Mohr circle tells you what is the maximum possible shear stress in that state of stress. So if I had a tiny Mohr circle over here, I know that there is a lot of compression, but there is no shear stress. But here I see two things. I see that this one is this far from the origin, and these are far apart enough to have this amount of shear stress. So if I kind of simplify this, I could say this is the center of the Mohr circle. This is the radius of the Mohr circle, right? And I can also say that that Mohr circle is equal to this Mohr circle, which is just a dot over there, located at the distance c, plus another Mohr circle with the radius r. Where this value over here is sigma 1 plus sigma 2 divided by 2. And this value over here is minus sigma 1 minus sigma 2 divided by 2. And this one is plus sigma 1 minus sigma 2 divided by 2. So I can decompose it. This is what is called the isotropic component of the stress tensor, and this is the deviatoric component. What is the mean stress of the deviatoric component. 0, right? If you calculate the mean stress, it's just going to be a dot over here. And this is going to be super important, as we're going to see later on, because rocks get stronger as you compress them more. The higher the effective stress, the stronger the rock gets. And you guys should be like rocks. Like the more stress you have, the stronger you get. If you do that, then you're going to do very well. Okay? Until you fracture, right? But you have to manage that, right? You have to manage that so you do not break like under stress. Okay. So let's do the same, but now mathematically and in 3 dimensions. But it's exactly the same. Now we have a vector, tensor sigma 1, sigma 2, sigma 1, 3, sigma 2, 3. I'm not writing the off-diagonal terms, okay, to save some time. The lower off-diagonal terms, because they are the same. I'm going to be able to write now that stress tensor as a tensor which is an isotropic tensor with 0 off-diagonal terms, in which I'm going to define sigma m as sigma 1 plus sigma 2, 2 plus sigma 3, 3 divided by 3. So all the diagonal terms, let me zoom out. All the diagonal terms, I add them up, I divide it by 3, and I call those sigma m. I had a professor of linear algebra who was a mathematician. He was proposing that this is not a simple equality, okay? This is a definition. We call it, we are defining sigma m as that. He was proposing that you should have a different sign, something like this, to define something. Some people use 3, but this guy was proposing this one. I don't know if he was coming up with that one, but he was saying, because the 3 one is also equivalent, right? So, probably I'm not that familiar with the 3 lines to define, but this is a definition. That's my point. Okay, so it looks like a D over there, right? So this is a definition, sigma m. And in order to maintain this as a equality, then what am I going to have over here? Can somebody tell me what is going to be the first term there? If I want, this one, when I add to that one to be equal to this is going to be sigma 1 minus sigma m. What about sigma 1, 2? It's going to be the same. Sigma 1, 3 is going to be the same. Sigma 2, 2 minus sigma m. Sigma 2, 3. Sigma 3, 3 minus sigma m. And same as before, this is going to be the isotropic component, and this is going to be the deviatoric component. And I can further, we already know the graphical part, so I'm going to cover that. I can further simplify this as vector sigma is going to be equal to sigma m times the identity tensor plus, I'm defining now what is this. I'm going to call it vector tensor ST, which is the deviatoric stress tensor. Okay? This is going to be very useful because it's going to allow us to calculate a very important property that we're going to see in a bit. Any question about this decomposition? Yes.
So because you're working with like your full effective stress tensor,
Yes.
sigma m isn't your confining pressure here, correct? Because you're not.
Let's try to forget a little bit about confining pressure, because confining pressure is a very convenient term for the lab, but it makes a lot of confusion when we talk about stress and pressure in the subsurface. Sometimes you may, confining pressure is used as an equivalent of total stress, but by now we know that stress is a tensor and there are 3 different values, so we cannot simplify like that. So this is the effective stress tensor. If we were to talk about the total stress tensor, it would be similar, but I want to work with the effective stress tensor because the strength of rocks is going to be judged in terms of effective stress, not in terms of total stress. And that's why I'm working almost exclusively now with effective stress. Okay, so we knew, yes, you have a question.
Here, the sigma m is not necessarily the average of the principal stresses.
Okay, we're gonna go in there right now. So I told you before that any tensor will have 3 real valued numbers which are unique to that tensor, which are called eigenvalues, right? Similarly to those, you can also calculate 3 other real valued numbers for a stress symmetric tensor, which are called the invariants. And why do you think they are called invariants? Because they are always the same, no matter what is the coordinate system. Invariant number 1 is going to be the summation of the diagonal terms. Also sometimes called the trace of the matrix. And it doesn't matter if this is the effective stress tensor in an arbitrary coordinate system, or if it is the effective stress tensor on the principal coordinate system, it's going to be always the same, because that's an invariant. So sigma m is also going to be equal to sigma 1 plus sigma 2 plus sigma 3, all principal divided by 3, because that value is an invariant. And from here also we could calculate sigma m is equal to the first invariant divided by 3 of the stress tensor, remember, okay? The second invariant of the stress tensor is going to be, this is an equation I never remember, but you don't have to remember either. We're not going to use it very often. Is the product of the diagonal terms minus the square of the off-diagonal terms. And the third invariant of the stress tensor is the determinant of the tensor. You guys remember how to calculate that? Yeah, I do, right? This one times this one times that one minus this one times that one.
Repeat two rows and then you do
Yeah.
three lines like this and minus three lines like that. And it works every time.
How is that? I don't know that method.
No.
You want to come up here? And,
Sure,
yeah.
you repeat the first two rows over to the side of the matrix.
Yeah.
So you rewrite, so if your matrix is A, B, C,
Oh,
D,
okay.
F, E, F, G, you write
Yeah.
on the right side A, B, D.
Okay.
So it's A, B, D, E, G, H.
Yeah.
And then you make the three full diagonal lines you can from left to right.
Yeah.
And you make the three full diagonal lines you can from right to left. And then it's the three ones left to right minus
That's
the three ones right to left.
that sounds kind of complicated. I'd rather use Python or MATLAB to
Well,
that.
yeah, but it's easier way to do it
Yeah.
by hand than
Yeah.
taking the determinants of all the potential 2x2 matrices
Yeah.
by the off one. 'Cause the
Wha-
other way is you take the determinants of all the 2x2 matrices and multiply them by a coefficient of the last
Yeah.
remaining term.
Well, what I do is I multiply sigma 1, 1 times the determinant of that, then sigma 1, 2 times the
Everybody has some.
determinant of that one, negative, and then sigma 1, 3 times the determinant of that one. Okay, doesn't matter. Okay, it's the determinant. But also, you know, actually we don't need these two. The most important invariant here is the first invariant of the stress tensor. However, there is another one that we can calculate. This is a tensor 2, right? We can calculate invariants of that tensor 2. So let me continue over here. We are not going to call those I, but we're going to call them J. So what is going to be the first invariant of the deviatoric stress tensor? 0. Very well. Everyone sees that? So let's look. That's SD, right? So you add up all the diagonal terms, and you're going to end up with minus 3 sigma m, and that's equal to adding up sigma 1, 1, sigma 2, 2, and sigma 3, 3. So that's going to be 0. The second invariant of the deviatoric stress tensor is an important one. And this one, you can, if you apply this equation to that one over here, you can get to something a little bit more simplified that looks something like what I'm writing right now. Is a summation of the squares of the differences between the principal stresses. So this one is very similar to what would be the analogy of J2 with the 2D case?
It's 1 over sigma, or no, it's 1 over 6.
1 over 6. Yeah, that's number 6. So let me bring the here we have the deviatoric Mohr circle, right? And how far apart sigma 1 and sigma 2 are quantified by the radius of the circle in the simple 2D case. In the 3D case, we use J2. You see this is the difference between the principal stresses. So how different those are, the bigger the difference between the principal stresses, the bigger J2 is going to be. So the equivalent for C is going to be I1, isotropic invariant, first invariant of the tensor, and the analogy for R is going to be J2, second invariant of the deviatoric stress tensor. And J3 we don't really care about that one, okay? That doesn't serve almost any purpose. So it's going to be the determinant of SD, but it doesn't tell us. Well, actually, no. Sometimes this one is useful. This one goes into some equations that tell you about the failure of rocks. But J3, no, not that much. All right, so let's try to understand what, and I have one more definition to do, why these are important, I1 and J2. We can make plots of I1 and J2. So,
I1 over 3?
and that's what, well, it depends. I mean, you can plot it I1 over 3 or I1, it depends on your equation. But let's just go with I1 and J2. Okay? This is almost the same as the Mohr circle, right? Because I1, captures normal stress, and J2 captures shear. Why we were drawing Mohr circles before? Let's say this is a Mohr circle. That doesn't look much as a circle. This is a Mohr circle. We care about that Mohr circle because we don't want to get that Mohr circle too big, because we know that materials, in our case rocks, they may fail if that circle is too big. So the shear failure line, let's say, is this one. That's the Coulomb criterion that says the shear stress cannot be higher than a certain constant plus normal stress times the tangent of the friction angle, where this is phi. If you go beyond the line, you go into failure or inelasticity. Very similarly to that, this one works just in 2 dimensions. Or if you were to plot a 3D Mohr circle, probably it might work more or less okay. But if you want to generalize this for 3 dimensions, instead of sigma n and tau, you use I1 and J2. And there is a similar line for that, in which you write your equation now as you say the maximum J2 is going to be equal to, say, a constant C naught plus a constant C1 times I1. And probably your state of stress, let's say it's not a failure, is somewhere over here. Probably you are familiar with failure criteria for non-stress sensitive materials. So rocks are stress sensitive. That's why as you increase I1, the J2 gets bigger. This is exactly the same what I was telling you before. The higher the effective stress, the stronger the rock. So this would apply to stress sensitive materials and also to rock. Probably you know that for metals at typical applications, J2 is a constant. So if J2 passes a certain threshold, you know that goes into yield. And this will be a criterion for the metal. Something that in the range of applications, typical engineering applications, it's independent of stress, of the mean stress. And this is very useful because as you load a rock or as you load a material, you can plot what is the stress path. So for example, here I could say at time 0, this one is here, but I know that as time increases, this one is going to move into that direction. So it's much easier to look at the stress tensor with these two quantities that we know that capture that stress tensor very well. And we're going to see that later on too, when we talk about stress path for reservoirs. And I also, I'm going to do a schematic in a minute. Yes?
Is this behavior the same for a porous rock and a non-porous rock?
The failure?
The line that you
Probably no. No, it would be mostly the same. But what do you mean? All rocks are kind of porous, right? And all of them are stress sensitive. There are some type of rocks or mud rocks that if you load them too quickly, you do something which is undrained loading, and they behave like metals. They are not sensitive to
for example, for
the
cement,
total stress.
for cement.
Cements are like this. Cements are stress sensitive too. Shales are stress sensitive. Okay, so let me do two more definitions, and then I'll go into an example. I1, J2 are kind of quantities that are meaningful, but are kind of difficult to, if I tell you the value J2 of something, you might not get it right away, right? Because it's in a square quantity, and the same with I1. I1 is just, the summation of the of diagonal terms, so it doesn't tell you much. Instead of that, we use two other parameters, which are called P and Q. And this P, in order to differentiate it from pressure, and meaning that it's an effective stress, we're going to call it P prime. P prime is going to be equal to what we defined before as sigma m, or what is the same as the first invariant of the effective stress tensor divided by 3. And Q is going to be equal to the square root of 3 times J2. We're going to use these two parameters later on in a theory that allow us to explain the behavior of rocks with plastic deformation. What did I write? Critical Statoil. Working too much with Statoil. You know that Statoil now is called Equinor, so they changed name. So I know why I wasn't thinking on Statoil. This is critical state soil mechanics. So it came from that, from soil, not from. So this theory later on, we're going to use it, and for that we need that definition because it's very